Welcome to Transient Heat Conduction. Today, we'll explore how temperature within a material changes over time when subjected to sudden thermal conditions. Unlike steady-state conduction, where temperatures remain constant, transient conduction deals with time-dependent heat flow. This topic helps us predict temperature changes during heating and cooling processes, critical in engineering applications like metal casting, electronics cooling, and thermal protection systems. Get ready to master key concepts like the lumped capacitance method, the Biot number, and transient solutions for different geometries. Let's dive in and build a solid understanding of transient heat transfer.
Let's clarify what you'll gain from this session. A strong learning outcome is clear, specific, and action-oriented. It helps you know exactly what skills and knowledge you'll walk away with. For example, instead of a vague goal like learn about heat transfer, we focus on specific methods like lumped system analysis, analytical solutions for 1D conduction, and semi-infinite problems. We also highlight practical tools like the product-solution approach for multi-dimensional conduction. Keep your learning goals focused. Know what to achieve, why it matters, and how you can apply it.
2. Understand the core difference. Let's start by making a clear distinction. In steady-state conduction, temperature stays constant over time. Nothing changes. But in transient conduction, temperature depends on both time and position. This makes the analysis more dynamic and realistic for processes like cooling and heating. We use the general transient heat conduction equation to describe this behavior. Partial T is equal to alpha gradient square T. Here, alpha is the thermal diffusivity, telling us how quickly heat spreads through a material. Focus on this simple contrast. Steady state is fixed, transient is evolving, and it will guide your understanding of real-world heat transfer problems.
3. Keep it simple with lumped system analysis. Sometimes you don't need to overcomplicate things. When temperature variation inside a solid is small enough, we can simplify the problem using lumped system analysis. The key is the Biot number. If Bi is less than 0.1, the internal resistance is low enough to ignore internal gradients. This is a shortcut that saves you from complex equations. We use a simple temperature-time relation that follows exponential decay, and you can quickly estimate the heat transfer rate with a straightforward equation. Focus on Biot number first. If it's small, lumped system is your friend. Simple, fast, and effective.
4. Focus on simplicity with semi-infinite solids. Sometimes we can simplify a complex geometry. Semi-infinite solids assume one exposed surface, while the rest stretches to infinity, making the math more manageable. You only need to focus on the surface behavior. Different boundary conditions give you quick solutions. Constant temperature, constant heat flux, and convective boundary. All of these are solved with a handy tool, the error function, or ERFC, for quick temperature predictions. Remember, if the solid is big enough and heat hasn't reached the other end, semi-infinite analysis helps you skip complex models and still get accurate insights. 5. Focus on 1D transient heat conduction. Let's make your analysis practical and focused. When heat transfer is mainly in one direction, we simplify it using 1D transient conduction. It works well for plane walls, cylinders, and spheres. The key is using the Fourier number to track time effects. With one-term approximation, you quickly estimate temperature profiles for different geometries using compact formulas. Don't overcomplicate with full series solutions. Focus on the dominant term and the role of Biot number in setting your constants. Simple, fast, and surprisingly accurate for engineering work.
6. Simplify complexity with multi-dimensional systems. Dealing with multi-dimensional heat flow, the product solution method keeps it simple by breaking it down into separate 1D solutions. Instead of solving complex equations in 2 or 3 dimensions, you multiply 1D results. This method is especially useful for rectangular blocks, short cylinders, and semi-infinite plates. You can also quickly calculate total heat transfer in 2D and 3D using easy-to-follow formulas. Don't get lost in complicated multidimensional math. Divide it, solve it, and combine it for fast, practical results. 7. Connect theory to real-world applications. Learning theory is great, but applying it makes it valuable. Transient heat conduction is everywhere. In your kitchen, your phone, and industrial plants. For cooking, we use lumped analysis for small foods and semi-infinite conduction for large meat cuts. In electronics, transient conduction predicts chip temperature spikes. In food freezing, faster freezing means better food quality by minimizing ice crystals. And in industry, we model metal quenching or laser heating with transient conduction. Always ask yourself, where can I apply this knowledge? That's where engineering comes alive. 8. Wrap it up with clear takeaways. We focused on practical tools like the lumped system when Biot is less than 0.1 and semi-infinite conduction for large bodies with surface-driven effects. The Fourier number tracks how heat moves over time, while the one-term approximation makes solving transient problems quick and easy. For complex shapes, we used the product solution method. And remember, this isn't just theory. You'll see it in food industries, metallurgy, and electronics cooling. Always end by asking, where can I apply this tomorrow?